So first let's talk about what dependent samples and matched pairs actually mean. In this section we develop methods for testing hypotheses and constructing confidence intervals involving the mean of the differences of the values from two dependent populations. With dependent samples, there's some relationship between the samples, where each value in one sample is paired with a corresponding value in the other sample. The pairs of values are called matched pairs. We use the same methods as inference on a single population mean, except that the differences between pairs of values are analyzed. Hypothesis testing for dependent samples. We will use sample data from two dependent samples to test a claim made about the differences between pairs of values. The population parameter is the mean of the differences. The requirements are: 1. The sample data are dependent. So in other words, the selection of one of the values from the pair depends on the selection of the other value from the pair. The samples are simple random samples. And 3, either or both of these conditions is satisfied. Either the number of pairs of sample data is large, meaning n is greater than 30, or the pairs of values have differences that are from a population having a distribution that is approximately normal. In other words, they either have to come from some population with a normal distribution, or we have to have a large sample size, such as something greater than 30. Here's the notation for dependent samples. And again, remember that in this case, we're actually going to find the differences between each pair of values, and then we're going to find the statistics for those differences. So D here is going to stand for the individual difference between two values of a single matched pair. So we take one minus the other, and that's our individual difference. Mu sub D is the mean value of the differences D for the population of paired data. In other words, if we could look at all the possible pairs and find the difference for each one, and then find the mean for those differences, that would be our mu sub D. D bar is the sample mean of the differences. In other words, when we take our sample, we'll have a certain number of pairs of values, we'll find the differences, and then from those differences we'll find the mean. Same thing with the standard deviation for the sample. This would be calculated from the list of differences, and we would just find the standard deviation for that list. And n is going to be our sample size, which is going to be the number of pairs of data. Now our test statistic, in this situation, this is based on a t-distribution, so it's t sub naught, and this one is going to look a lot like the test statistic we had when we were talking about a single population and testing a mean. So here we're going to have our sample mean of the differences, which is d bar, divided by the standard deviation of the differences over the square root of our sample size. And in this case, since we're using the t-distribution, we need to know the number of degrees of freedom. That's still going to be n minus 1. Here's an example. The following data represent the cost of a one-night stay in Hampton Inn Hotels and Quinta Inn Hotels for a random sample of 10 cities. Test the claim that Hampton Inn Hotels are priced higher than Quinta Hotels at the alpha equals 0.05 level of significance. Now, why does this count as dependent samples or matched pairs? Because we have a list of 10 cities, and in each city we got a price for Hampton Inn and a price for La Quinta. So, for example, here, the selection of the La Quinta Inn in Dallas depended on the fact that we had already selected a Hampton Inn in Dallas. So the city was selected for the Hampton Inn, and then we had to select a La Quinta in the same city. So these values are matched in some way to these over here. Step 1 in our hypothesis test is to write our claim, and that is that Hampton Inn Hotels are priced higher than La Quinta Hotels. And we need to define the two populations. Since we mentioned Hampton Inn first in the claim, we'll just define Hampton Inn as population 1 and La Quinta as population 2. This means that we'll calculate the differences between paired values as the Hampton Inn value minus the La Quinta value. The parameter is the mean of the differences, which is mu sub d. And now what inequality should we use? The claim says that Hampton Inn is priced higher than La Quinta. This would mean that the differences, Hampton Inn minus La Quinta, would be positive on the average. This translates to a greater than. So we would write our alternative hypothesis as mu sub d is greater than 0. So here's our alternative hypothesis. H sub 1 is that mu sub d is greater than 0. Our null hypothesis, we just replace the inequality with an equal sign, so we get mu sub d is equal to 0. Now for step 2, if we think about a type 1 error, this would be supporting the claim that Hampton Inn Hotels are priced higher than La Quinta Hotels when this is not actually true. This error could potentially lead to a loss of business for Hampton Inn. The significance level was given for this problem already, and that was alpha equals 0.05. So for step 3, we first need to calculate the difference for each pair of values. So here we have our Hampton Inn minus our La Quinta price, and in each of these we found the difference between the two values. And just when you're doing this, remember, whichever way you decide to do this, you take your value from population 1 minus your value from population 2 to get your difference. So because we were subtracting the 129 minus the 105 here, then down here we're taking the 109 minus the 119. And notice that here we get a negative value because in this case the Hampton Inn price was actually lower than the La Quinta Inn price. So to continue step 3, we need to calculate the sample statistics, that is the sample mean and the sample standard deviation of those differences. So we take our column of differences, and that's our list of numbers, and we're finding the sample mean and the sample standard deviation. So the mean of the differences, that's d bar, is 31.4, and the standard deviation is s sub d equals 17.3. The sample size is the number of pairs, and that would be 10. So our test statistic, again it's t sub naught, is 31.4 divided by 17.3 divided by the square root of 10. That turns out to be 3.44. For step 4, since the alternative hypothesis had a greater than, that makes this a right-tailed test. And we're using the t-distribution this time, so here's our picture. We have our t-distribution with t equals 0 in the middle. Here is our test statistic, and since this is a right-tailed test, we are shading from our test statistic to the right. Now our p-value is going to be the area of our shaded region. Since this is a t-distribution, we want to use the t-CDF. So this is going from 3.44 up to a large positive number, say 1,000, and then we have to put in our degrees of freedom, and remember that's n minus 1. Since our n was 10, this would be 9. The p-value here turns out to be 0.0037. Comparing the p-value to alpha, we have 0.0037 is less than or equal to 0.05, which is true. That means we have positive conclusions. So our conclusion regarding the null hypothesis is that we do reject H naught. Now for step 5, writing our final conclusion, this again would be positive, so we'd say there is sufficient evidence to support the claim that Hampton Inn Hotels are priced higher than La Quinta Inn Hotels. So what we're doing here is obtaining a confidence interval estimate of the mean of the differences. So for a confidence interval estimate, our point estimate is going to be the d bar, which is going to be in the middle of our confidence interval, and from that value we're going to subtract the margin of error to get our lower limit. We're going to add the margin of error to get our upper limit. And the margin of error here, again, this looks very much like the margin of error formula we had for one sample confidence interval for a mean. So we have t alpha over 2 times the sample standard deviation of the differences divided by the square root of n. And again, we have n minus 1 degrees of freedom. So here's an example. We're going to use the sample data given in the preceding example to construct a 95% confidence interval estimate of the population mean difference between the prices at the two hotels. So again, our point estimate was D bar, and that's $31.40. For a 95% level of confidence with 9 degrees of freedom, our critical value we would find by doing inverse t of 0.025 with 9 degrees of freedom. That gives us a negative, so we just take off the negative, and that turns out to be 2.26. So our margin of error is 2.26 times our sample standard deviation, which was 17.3, divided by the square root of 10, and that gives us $12.40. So our confidence interval actually is $31.40 plus or minus $12.40, which gives us a lower limit of $20 and an upper limit of $43.80. Our interpretation would be we are 95% confident that the mean difference between prices at the two hotels is between $20 and $41.80. So again, this tells you something. If you're thinking about going and getting a room at either Hampton Inn or La Quinta, this tells you that if you go to Hampton Inn, you're going to be paying between $20 and $41.80 more than you would at a La Quinta Inn in the same city. And again, we look at whether the confidence interval includes 0. In this case, it doesn't. So that does imply that there's a significant difference between prices at Hampton Inn and La Quinta. The confidence interval suggests that the prices are higher at Hampton Inn than at La Quinta. And again, if the confidence interval did include 0, that would be saying there's a possibility that the difference between the two is 0, which would be the same as saying that they're the same.